Over 50 years ago, orange soil was discovered on the moon, with this creating interest from a variety of companies. Based on discussion from the client, we were tasked with the challenge of creating a TRL-3 prototype lunar rover robot capable of collecting at least 3 samples. As EGB320 was also interested in analysing unweathered samples, it was also important that the robot could flip rocks and bring these samples back to the lander test facility.
We have created an automated lunar rover to find and return samples around the environment. The following is a list of a few implicit and explicit requirements our rover has been designed to complete. We can drive around the environment, like up and down the elevated lander. We can search the map without driving into obstacles. We can find samples out in the open, and we can search under rocks and retrieve the samples.
Along with this, the robot was not to exceed a CubeSat 1.5 form factor, a weight of 1.3 kilos, and a product budget of no more than $185.
Hi, I'm Christopher, and I'm responsible for the vision subsystem of Group 25's robot.
The vision system takes live video data from a Raspberry Pi camera and identifies objects in the image by thresholding according to color and brightness. Camera data is recorded using the Raspberry Pi camera module, and image processing is performed by many functions from the Computer Vision's OpenCV toolbox. The outer edges of visible objects are stored as contours and used to create external boundary boxes for data analysis. Information is then calculated on each object, including distance and bearing of each of the objects. This data is displayed visually for the user and passed directly to the navigation subsystem. In order to improve reliability of the vision subsystem, settings such as camera exposure speed and white balance of the image are held constant at values optimized for the arena lighting conditions. Other solutions were considered, such as dynamically adjusting the color thresholding values and using OpenCV's blob detection method, but the final solution was consistent camera settings.
Hello guys, my name is Sarl. I'm in charge of the navigation subsystem.
A potential fields method is used for driving around, tracking, and avoiding objects. This system has been designed to get data from the vision system and use the mobility system to drive around. The potential fields method is paired with a custom searching algorithm which drives around the lander, scanning for rocks or samples. Using the sample collection system's commands, the navigation system collects covered and uncovered samples from the environment.
Hi, I'm Jake and I'm responsible for the mobility system.
The type of mobility system we chose to implement was a 2-wheel system with a caster wheel for balance. This design allowed us to keep the robot simple but still very effective. The motors were chosen so that it would have high enough torque to climb the 15-degree lander incline and have an RPM slow enough to achieve a slow speed of under 5 cm per second. Pololu micro metal gear motors were used as they were reliable and did not cost too much. Forward and reverse operation of each motor was achieved by using pulse width modulation signals from the Raspberry Pi, driven by dual H-bridge motor drivers. Python was used to code the robot, and for movement, vector addition and subtraction was used, allowing the robot to drive and turn at the same time or independently.
Hi, I'm James, and I was responsible for the sample collection subsystem of the robot. The sample collection subsystem was designed to both collect samples in the open, along with flipping rocks to reveal covered samples. The final concept was developed after various iterations, with a number of key factors considered. To effectively flip the rock, the system was designed to allow the mechanism to rotate more than 45 degrees, with this allowing the rock to fall over and uncover the sample. Along with this, the shape of the flipper was modified to both reduce the weight and cost, along with preventing the lunar surface from catching on the corners of the mechanism. Another design consideration was the curvature of the collection scoop. Ensuring this was angled towards the center of the robot has successfully proven to sweep the samples towards the center, no matter of the robot's position to the sample. Along with this, a number of custom PCBs were designed. These ensured the robot integrated seamlessly together, with a power distribution board for regulating power to all parts of the robot, along with a custom Raspberry Pi motor shield useful for sending GPIO commands to both the servo and motor driver. This was then integrated into the developed system architecture.
The vision subsystem is able to effectively segment individual objects within the arena and produce accurate distance and bearing measurements. Upon being called, the vision subsystem could run at frequencies of greater than 10 Hz and up to 80 Hz.
The navigation system has achieved the following. The system accurately collects covered and uncovered samples while avoiding obstacles using the potential fields method. The system searches around the lander and tracks samples or rocks when they're seen using the custom searching algorithm.
By the final demonstration, the robot was able to achieve the slow speed required and was able to consistently move up and down the lander and was able to spin on the spot.